All right, hello everyone. This video will be a review of all of the material covered in the electromagnetic radiation unit of Physics 30. One of the first things that we talked about in this unit was a model of electromagnetic radiation that explains the energy being propagated by things like light and X-rays and gamma rays as being wave-like in nature. And Maxwell came up with this idea. He proposed the idea that a changing electric field will produce a changing magnetic field. The key words here are changing, and also that a changing magnetic field will produce a changing electric field. These are collectively what we call Maxwell's principles of electromagnetism. If you have a changing electric field that produces a changing magnetic field, but a changing magnetic field will automatically produce a changing electric field, then this is a series of events that keep feeding off of each other. And together, these electric fields and magnetic fields that are being created are what Maxwell calls an electromagnetic wave. And in an electromagnetic wave, the electric field, the magnetic field, and the direction of what we call propagation, but that just means the direction that the wave is moving, are all perpendicular to one another. And we visualize this wave. This is just a snapshot of the wave. We visualize it at some point in time as looking like this. So the electric field is the blue part of the electromagnetic wave, and it's oriented vertically. The magnetic field is the red part on this diagram, and it's oriented horizontally, and the wave is traveling to the right. So those three directions, vertical, horizontal, and to the right, are all perpendicular to one another. Continuing with Maxwell's principles of electromagnetism and the electromagnetic wave that they predict, in order to initiate this process, in order for you to create electromagnetic radiation, usually you can accelerate a charge. And I want to just amend what I just said and make sure that you understand that any accelerating charge will produce EMR. There are other ways to produce EMR, but if you have a charge that's accelerating, EMR will be produced. Essentially, anytime you have a changing electric field or a changing magnetic field, you're going to produce EMR. I've got in brackets here, we can either have a charge being accelerated, or you can have a charged particle lose energy in what's called a quantum change. And later on in the course, we learned about electron transitions in atoms and how they produce visible light, ultraviolet radiation, and infrared radiation. That's what I'm talking about. Or in the case of X-rays, and I'll go over all of these forms of EMR in a second, but X-rays are produced by a high-speed electron suddenly being stopped by a metal target. So that is considered a quantum change. All of that energy is lost in an instant, and it changes into, well, an X-ray photon. So again, whenever you have an electric field that's changing or a magnetic field that's changing, you will produce EMR. And this model of EMR is very important because the only way that you can explain diffraction of light or interference of light, or diffraction and interference of other forms of EMR, is to use the wave model of electromagnetic radiation. We contrast that with what's loosely called the particle model of EMR, which is really the photon model of EMR. And this was proposed by Planck and Einstein together, and what it says is that electromagnetic radiation, whether it's light or gamma rays or infrared radiation or radar or microwaves, all of these forms of electromagnetic radiation are composed of little discrete, in other words, quantized bundles of energy, which we refer to as photons. And this model of EMR is necessary for you to explain things like the photoelectric effect and the Compton effect. And this is almost always a pet question on diploma exams. That the wave model of EMR is needed to explain things like diffraction and interference whereas the particle or photon model of EMR is required to explain the photoelectric and Compton effects. So when you take a look at light coming out of a laser, according to Maxwell's electromagnetic wave model, what we have is a wave of energy, a continuous wave of energy traveling out of the laser. However, when you talk about Planck and Einstein's photon model of EMR, this is what we can imagine is happening. All of these little bundles of light energy are streaming out of the laser one after the other. On the front of your unit handout, I had put this graphic, and this illustrates a very important idea with light, or EMR in general, and it's that sometimes it behaves as a particle and sometimes it behaves as a wave. There are different types of electromagnetic radiation. We've learned that there are 7 main groups. I suppose you could subdivide these and maybe even find other groups to add. But going from low frequency, we have radio waves, microwaves, which are also known as radar, then infrared radiation, visible light going from red to violet, then ultraviolet radiation, X-rays and gamma radiation. And you were expected to know the order of these in terms of wavelength and frequency. So radio waves have a very long wavelength and a small frequency, whereas something like gamma radiation has a high frequency and a short wavelength. Other things that you're expected to know about all of these forms of electromagnetic radiation are typical wavelengths. So if I tell you that we have a form of EMR of wavelength 35 nanometers, you should know that that's ultraviolet. If I say it is a wavelength of 1 times 10 to the negative 10 meters, you should know that's X-ray. If you are given the frequency and you're not familiar with the range of frequencies of these types of radiation, then I would highly recommend finding the wavelength that goes with that frequency, and I'll talk about that and how to do that in just a second. All of these forms of EMR travel at the speed of light. So if you're dealing with a problem that has microwave radiation, you should know that in a vacuum or in air, the speed of the microwaves is 3 times 10 to the 8 meters per second. Should be able to put these in any order, ranging from low frequency to high frequency, or from short wavelength to long wavelength, or even in terms of photon energy. And since the energy of a photon is proportional to the frequency, gamma radiation has the highest photon energy. You also are expected to know, even though you might not be asked all of this, you're expected to know how each form of EMR is produced, and also what some common uses of them are. And finally, you should be able to use your universal wave equation. The universal wave equation says that the speed of the wave is equal to the frequency times the wavelength. So earlier when I said if you know the frequency and want to find the wavelength so you can classify it, this would be the formula you would use to convert the frequency into a wavelength. For the speed, you would simply use the speed of light. All of these forms of EMR travel with uniform motion, so we could always use speed equals distance over time. And since they are all waves, we can relate the frequency of each of these to what's called the period of the wave. We learned in this course how to determine the speed of light, and I'm not going to go through all of the methods, but essentially they all require measuring a distance and measuring a time. And you're expected to be able to compare the accuracy of different experimental methods for determining the speed of light. Obviously, if you want to get a very accurate result for the speed of light, you need to do at least one of two things. One, have the light travel a very, very large distance, and be able to measure the time of travel very accurately. One type of experiment is Michelson's rotating mirror experiment. Make sure you go back in your notes and try a couple of these problems. Very often they are on the diploma exam. Just a note here, when you do an analysis with Michelson's rotating mirror experiment, you're going to say speed equals distance over time. The distance is the distance between the rotating mirror in the experiment and the fixed mirror, and the time is the time for 1/8 of a revolution. Now I want to be careful here. It's 1/8 of a revolution because this is an 8-sided mirror. If you were given on an exam a Michelson's experiment with a 10-sided rotating mirror, then the time at the bottom of the screen would be the time for 1/10 of a revolution. We now get into optics. The law of reflection says that the angle of incidence of a reflected beam of light, or electromagnetic radiation, will always be equal to the angle of reflection. An angle of incidence is always measured between an incident ray of light and the normal line, and an angle of reflection is always measured between the reflected ray of light and the normal line. The takeaway from this is that optical angles, whether you're dealing with reflection or later with refraction, they are all measured relative to a normal line. And the normal line is simply a line that's perpendicular to, in this case, the mirror. Ray diagrams for curved mirrors. So it is an expectation that you can draw ray diagrams for curved mirrors. Since there's no written response on the diploma exam, what that translates to is you are expected to be able to pick out of a lineup of 4 choices what a ray diagram would look like. I'm going to go one further and say that ray diagrams are very useful because if you are good at drawing ray diagrams, you can determine the properties of an image very, very quickly and answer multiple choice questions. However, to begin with, one type of mirror is called a concave mirror. It's what I like to call a converging mirror because it takes parallel beams of light and converges them to a specific point. That point is called the focal point, and it is a positive focal point or a positive focal length. The other type of mirror is called a convex mirror, which I prefer to call a diverging mirror. And those have negative focal points or negative focal lengths. What a diverging or convex mirror does is it takes parallel beams of light and reflects them away from each other. It's useful for you to note that a concave mirror can produce real images or virtual images. However, a convex mirror will always only be able to produce virtual images. To draw a ray diagram, what we're looking at here is a curved mirror, which is a concave or converging mirror. The object is on the left, and you need to know the paths of the following beams of light. The blue beam of light leaves the top of the object parallel to the axis of the mirror, and it will always reflect through the focus. The green beam of light leaves the top of the object, and it will go through the focus, and it will reflect parallel. And the red beam of light is leaving the top of the object, going through the center of curvature, and it reflects back through the center. Where any 2 of these 3 beams meet is where the top of the image will be. And by the top of the image, in this case, it's actually at the bottom of the diagram because the image is inverted. When you're talking about a convex mirror, a parallel beam of light, which is blue, will reflect away from the focus. A beam of light that is heading towards the focus, which is the green beam of light, will reflect parallel. And the red beam of light is heading towards the center. It will reflect back to the center. And the image is produced and defined by where those beams of light meet. And that image is a virtual image for a number of reasons. We will get into this again later, but for now, real images are always inverted, and real images can be projected onto a screen. So when you take a look at the top diagram, if I put a screen in front of the mirror, in this location, then what I will see on the screen is the image of the object, and it will be upside down. And these are labs that we've done in class. If I put a screen over here, I'm not going to see anything. And that's because this image on the bottom of the screen is behind the mirror. And if it's behind the mirror, it doesn't actually exist. It's called a virtual image. And what you're seeing when you look in the mirror is basically an optical illusion. If I were to put a screen on the left-hand side of the mirror, I will not be able to project that image on the screen. So real images, which there's an example of one at the top of the page, are inverted and can be projected onto a screen. Virtual images, like the one at the bottom of the screen, are erect and they cannot be projected onto a screen. Refraction in Snell's law, when you have a light beam refracting, that means you have an incident ray of light leaving one medium and going to a different medium. During refraction, the speed and the wavelength of the electromagnetic wave change, but the frequency remains the same. If the AMR refracts towards the normal line, then the speed and the wavelength both decrease. And then the opposite is true. In the diagram I've illustrated here, there's the normal line, so you can see that the beam of light is refracting towards it, which means that this medium down here, this medium that the light is entering, is more optically dense than the medium that the light was in to begin with. A couple of other notes about this diagram. This is what's often referred to as the interface. Sometimes it's called the boundary. And of course, theta 1 and theta 2 are the angles of incidence and refraction, and they are always measured between the beam of light and the refracted. Pardon me. They are always measured between the beam of light and the normal line. So the angle of incidence, which is this, is measured between the incident ray and the normal line. The angle of refraction, which is this, is measured between the refracted ray and the normal line. Of course, we have Snell's law, which relates, and Snell's law appears on your formula sheet in two forms. One is n2 over n1 equals sine of theta 1 over sine of theta 2. So that relates the indices of refraction, n, of each media to the angle of incidence and the angle of refraction. You also have the second version of Snell's law, which says n2 over n1 is equal to v1 over v2, which is equal to lambda 1 over lambda 2. By the way, just a note, not all of the light is going to be refracted. There will always be some reflection off of a surface. Total internal reflection. First of all, this can only occur if the index of refraction of the second medium is smaller than the index of refraction of the first. That means it's going from some medium into a less dense medium. So light traveling from water to air has the opportunity of undergoing total internal reflection. It doesn't have to experience total internal reflection, but it's a possibility. We'll get to the condition that's necessary for that in just a second. The angle of incidence, well, there it is. The angle of incidence has to be greater than what's called the critical angle. So if the critical angle for light going from water to air is 48 degrees, if the angle of incidence is more than 48 degrees, then total internal reflection will occur. How do we find a critical angle? Well, the critical angle, and I'll show you some diagrams in just a second, a critical angle occurs when the angle of refraction is 90 degrees. So going with that, if you look at Snell's law, n2 over n1 equals sine theta 1 over sine theta 2. If we change sine theta 1 to sine of the critical angle, we're going to change theta 2 to 90 degrees. Because the critical angle occurs when the angle of refraction is 90. If you were to figure out what the sine of 90 degrees is, you would get 1. So this becomes n2 over n1 is sine of the critical angle. This formula that we're looking at on the bottom of the screen is not on your formula sheet. It's simply a derivation or an application of Snell's law. And you need to know how to determine it so you can solve problems with total internal reflection. So if angle 1, theta 1, which is the angle of incidence, is smaller than the critical angle, then you are going to get refraction, and it will be away from the normal because the light is traveling into a less dense medium. If the angle of incidence is more than the critical angle, then you're going to get total internal reflection. But don't forget, this line that I'm going to highlight, this line that I'm highlighting is the interface or boundary between the two media. And what that means is if it's going, say, from water down at the bottom to air up at the top, is that the light reflects 100% back into the water. And that's why we call it total internal reflection. If theta 1 is exactly equal to the critical angle, then in principle, neither refraction nor reflection occurs, but what happens is the beam of light is bent along the interface. And that's why we have 90 degrees for theta 2 when we use theta 1 is the critical angle. Dispersion of light is simply the process of taking white light, allowing it to pass through a prism. You should know that white light is composed of a continuous spectrum of colors. The range of wavelengths for those colors are approximately 400 to 700 nanometers. You may have been told that it might be a little bit less than 400 to a little bit more than 700, but we like to just stick with 400 to 700. It is expected that you know that 400 nanometers is violet and 700 is the red end of the spectrum. The reason why this happens is different wavelengths of light have different indices of refraction. The index of refraction for violet light, which is n, the index of refraction for violet light is a bigger number than the index of refraction for red light. And because of that, the violet light undergoes a greater amount of refraction. So it's bent more than the red. And as a result, you get this spreading out of the colors. I'm going to go through the ray diagrams for thin lenses, which work on the principle of refraction. Very similar idea to what we talked about with mirrors. Converging lenses, which we can loosely call convex, but they should be called converging, have positive focal lengths, whereas diverging lenses have negative focal lengths. Similarly, just like a converging mirror, which is called a concave mirror, just like a converging mirror can produce real or virtual images, so can a converging lens. And just like a diverging mirror, and a diverging mirror is convex, just like a diverging mirror can produce only virtual images, diverging lenses only produce virtual images. Again, I think it's useful to familiarize yourself with the ray diagrams because you may be asked to identify a correct ray diagram on an exam, or you may be asked a multiple choice question which can very quickly be answered by doing a ray diagram. For converging lenses, beams of light parallel to the axis refract through the opposite focus. Beams of light through the center continue through the center. Beams of light through the focus on the side of the lens that the object is on refract parallel. And again, where those beams of light come together, which is right here, define the top of the object, which in this case is upside down because it's a real image. You don't have to draw all three beams of light. Any two beams of light will meet where the image is formed. With a diverging lens, you should know that a beam of light going through the center continues through the center. A beam of light parallel will refract away from the focus closest to the object, and a beam of light going towards the opposite focus will refract parallel. And if you trace those beams of light back, if you trace this beam of light back, and this beam of light back, and this beam of light back, your brain is deceived into believing that there's an image over here where they appear to originate from. And that image is called a virtual image. Same thing that we talked about with mirrors. Real images are always inverted and they can be projected onto a screen. Virtual images are always erect and they cannot be projected onto a screen. Now that we've gone through mirrors and lenses, a quick review of the equations. There are your thin lens equations and mirror equations. You can use these for either mirrors or lenses. But there are some rules, and you have to stay within the confines of these rules. One of them is that anytime you're dealing with something that has a real focal point, the focal length is positive. And anytime you're dealing with something that has a virtual focal point, you have a focal length that's negative. So for example, going back to what we talked about before, concave mirrors have real focal points. So if I'm told that the focal length of a concave mirror is 12 centimeters, then I'm going to use positive 12 in the formula. However, convex mirrors have virtual focal points, so they have negative focal lengths. In other words, if I am told that the focal length of this mirror at the bottom of the screen, if I'm told the focal length, which is this distance from here to here, if I'm told that's 12 centimeters, then the number I put into the formula is negative 12 centimeters. The same is true, of course, for lenses. Converging lenses have positive focal lengths. Diverging have negative focal lengths. So the bottom line is any converging device has a real focal length. Converging devices have real focal lengths. Converging devices have real focal lengths. That's why it's more useful to think of lenses and mirrors not in terms of shape, but instead in terms of what they do to parallel beams of light. On the other hand, of course, we can do the same thing, that any kind of diverging device will have a virtual or negative focal length, and a diverging lens will have a negative or a virtual focal length. Getting back to our properties of the numbers for the equations for lenses and mirrors, real images always have a negative height. And to me, that kind of makes sense, because if you remember that real images are always inverted, the height is negative because they're upside down. And a positive displacement of the image. And I'm not sure I put this anywhere in this note package that you're looking at, but HI and DI are always opposite. One's positive and one's negative all the time. Virtual images, on the other hand, so HI is negative because it's inverted. Virtual images, HI is positive because the image is always erect, which means in the same orientation as the object. So it's, for lack of a better word, it's right side up. But if HI is negative for a virtual image, DI is positive, pardon me. But if HI is positive for a virtual image, then DI is negative. They are always opposite. This is not necessary to know, but boy, it's helpful. The virtual image produced by a diverging device will always be smaller than the object, whereas converging devices, which can produce virtual images, will produce virtual images when they do that are always larger than the object. In Physics 20, you learn about diffraction of mechanical waves. Here I'm talking about light waves and light energy, even though I may not use the word light specifically. And by an extension, I guess I'm talking about electromagnetic wave energy or electromagnetic waves. What diffraction is the spreading out of a wave as it passes through an opening. In order for diffraction to occur, the opening needs to be basically the same size as the wavelength or smaller than the wavelength. And as the opening gets smaller in relation to the wavelength, the more severe the diffraction is. So the more the wave or the light will spread out. What that means, since you're comparing the size of the opening compared to the wavelength, is that long wavelengths will diffract more than short wavelengths. And I want you to think very carefully about what I'm about to say. The opposite is true for refraction. If we go back and we take a look at dispersion of light and the refraction of light, you can see that the violet light, which is the short wavelength in visible light, refracts a lot. It is deviated most from its path compared to all of the other colors. So with refraction, which is what's happening on this screen, the short wavelength is affected most. Whereas going back now to diffraction and interference, the long wavelength experiences the greater effect. So red is diffracted more than violet. We talk in class about what's called the Poisson or the Arago spot. It's just an example of diffraction in action combined with interference. When you have beams of light striking a solid disk, the beams of light that hit the edge of the disk will diffract. They will curve around the edge of the disk, and they meet at some common point, producing a bright spot due to constructive interference. And that bright spot is an example of interference. This diagram and this concept of the Poisson spot, or what we call the Arago spot, is really evidence for light being a wave. Speaking of interference, when you shine a laser light or what we call a monochromatic beam of light through a pair of two openings, you get an interference pattern. I don't think it's important in this review to get into the mathematical geometry of why this happens, but you get a series of bright spots on a screen. And you would have seen this in numerous demos and lab work that you do. These bright spots are called antinodes, or simply maxima, or bright spots. And the points in between the bright spots are called nodes, or that should say dark spots. Notice that this center dot, or spot, the central maximum, is the brightest or most intense. Most of the light is there, and then as you go further and further away from the center, the brightness kind of peters out. You should be able to use your double slit interference equations. They're called Young's double slit experiment equations. The wavelength of the light used is d sine theta over n, or the wavelength is equal to xd over nl. This second formula you should know that you can only use for angles less than about 10 degrees. Briefly here, d is the distance between the slits. I don't know if you can tell on the video you're watching, but if you look at where my cursor is, I'll highlight this for you. This is the material that has a double slit in it, and if you look very carefully, there's two tiny openings. Lambda is clearly the wavelength of the light. Theta is the angle between a particular beam of light that you're looking at. Whether you're looking at the central maximum or one of the others, theta is the angle between that horizontal line and the beam of light you're looking at. N refers to, it's called the order. If you're looking at the first maxima after the central on either side, n is 1, and as you move further away, n is 2, and then n would be 3. And x is the distance from the central maximum, which is n equals 0, to whichever n you're talking about. L, of course, is the distance between the screen where you're seeing the image and the diffraction grating or the double slit. So longer wavelengths will produce greater angles, smaller wavelengths will produce smaller angles, and smaller values of d increase the amount of diffraction so the angles go up. If you've got a bright spot, you're going to use integral values of n, and if you have a dark spot, you're going to use half integral values of n. So you're going to use 0.5 or 1.5 or 2.5, etc. This is by far the best evidence that shows that light is a wave, the fact that it can diffract and interfere. By the way, one other thing that's not in this package, sometimes you're given the specifications of a diffraction grating, and they might be given to you in lines per meter. In order for you to find d, you take the reciprocal of that to get meters per line. All right, polarization of light. Just to begin with, polarization provides direct evidence that light is a transverse wave. So we've established that light is a wave due to the fact that it diffracts and interferes. As soon as you can get that wave to be polarized, then you're saying it's transverse. If you take a beam of light and the light coming off of that light bulb is oriented in a number of different directions. Some of the light is oscillating up and down, some is oscillating horizontally, some is oscillating at angles in between those two directions. And you pass it through a vertically oriented polarizer, which, by the way, this diagram showing the vertically oriented polarizer is not what it would look like. That's cartoonish in nature. You would never see these openings. When that light passes through that vertically oriented polarizer, anything that is not oscillating vertically gets knocked out by the polarizer. So this light in the center is vertically polarized light. If I end up passing that through now a horizontally oriented polarizer, then I will get zero transmission, because this second polarizer will knock out everything except for horizontally oscillating light. So it's going to knock out the vertical light. The minimum transmission of light, which means the minimum amount of light getting through, is always going to happen when these two filters are perpendicular to one another. Blackbody radiation, Planck, and quantization of energy. So Planck proposed that energy was quantized. There was this thing called the Blackbody radiation problem. And here's a graph showing the problem. When physicists around 1905 predicted the distribution of wavelengths for a black body, which is a glowing solid, they were successful in predicting what actually happened if the temperature was about 3,000 degrees Kelvin or about 4,000 degrees Kelvin. But when you hit around 5,000 degrees Kelvin, the prediction was this dotted line. But what you would observe in a lab is the red line. So there's obviously a disconnect here between the physics they were using, which is the prediction, and the observation that they see in the lab. All I'm saying up top is that by proposing that energy is quantized, that tweaks the physics prediction to match the observation. It was Einstein that actually took this a little bit further and said not only is energy, in a general sense, quantized, but light energy specifically, or electromagnetic energy specifically, is quantized, and those quanta of energy are called photons. So the energy of a photon can be found by either the frequency of the electromagnetic radiation or by the wavelength. HF is the energy of a photon, or HC over lambda is the energy of a photon. All right, the photoelectric effect. The photoelectric effect is huge in this course. Sometimes there are 4 or 5 maybe even 6 questions on the diploma exam that are connected in some way to what's going on in the photoelectric effect. First of all, what the photoelectric effect is, light incident on a metal surface ejects electrons from the metal. You'll notice I've said EMR in general because it could be ultraviolet radiation or other forms of EMR, maybe even infrared under certain circumstances. There's a condition that has to be met for this to happen. However, this is what the photoelectric effect is. So when you have a solar cell, what's happening is it's absorbing light and it's ejecting electrons, and we're producing electricity from the energy that those electrons have. The condition is this: the light that's striking the metal surface, or the EMR that's striking the metal surface, has to have a minimum frequency. We call that the threshold frequency. And each metal has its own threshold frequency. So light that might cause electrons to be ejected from sodium might not cause electrons to be ejected from aluminum. Take a look at the electromagnetic spectrum in terms of photons. I've got my visible light spectrum, Roy G. Biv. I've got a red photon, an orange, a green, a blue, and a violet. I'm missing a yellow and I'm missing an indigo, but you get the idea. To the left on this of the red, I have infrared, and to the right of the violet, I have ultraviolet. I've just chosen the colors of gray for infrared and ultraviolet because they don't really have colors because we can't see them. They're not visible. When I say the light must have a minimum frequency, which is called the threshold frequency, and by the way, the threshold frequency is F0. What that means is if the threshold frequency of a particular metal is here, in this location, and I'm going to add an arrow so you know what I'm referring to. If I say the threshold frequency is here, that means infrared photons and red photons and orange photons and green photons will not cause the photoelectric effect to occur, whereas violet photons and ultraviolet and X-ray photons will. And if you take a look now at the bottom of the screen, what I'm saying is if the photon frequency is less than the threshold frequency, the photoelectric effect does not occur. On the other hand, if the frequency of the photon is greater than the threshold frequency, then the photoelectric effect does occur. So, if we have a different metal, and the threshold frequency of the different metal is over here, now what happens is green photons and yellow photons do cause the photoelectric effect to occur, but orange still does not. And violet continues to do so, and so does ultraviolet. I'm getting a little bit ahead of myself, but the reason this happens, and I will come back to this in a few minutes, the reason that the photoelectric effect does not occur if the frequency is smaller than the threshold frequency is that the energy that each photon has in the light is smaller than something called the work function of the metal, which is how much energy is needed to remove the electron from the metal. If the work function is how much energy is needed to remove the electron from the metal, if the photon energy is more than that, then it has more than enough energy to eject the electron. And by the way, since energy equals Planck's constant times frequency, this is the reason why if the photon frequency is greater than the threshold frequency, that's the reason why the photon energy is greater than the work function. A couple of other points about the photoelectric effect before we get into calculations. The brighter the radiation that's incident on the metal, the more electrons are ejected. And by the way, we measure more electrons being ejected by seeing a greater photoelectric current. As well, you should note that the brighter the radiation is a different way of saying the more light. So brighter light means more light. So a brighter light source has more photons, and that means that more electrons will be absorbing more photons in the photoelectric effect. So if I have a metal and I'm shining green light on the metal, and that green light has a great enough frequency, then what's going to happen is electrons will be ejected from the metal. Pretty straightforward. If I take that same metal, but I use twice as much light, so it's the same frequency, which means the same color, but I've actually got twice as much light hitting the metal, then I'm going to get more electrons being ejected. Specifically, I'll get twice as many electrons. And that's because I have twice the brightness. So the current will be twice as great. Putting this all together, here's what the photoelectric effect is. When light is incident on the surface of a metal, the light is absorbed and electrons are ejected. Each photon in the light is absorbed by a single electron. The electron uses some of the energy that was given to it by the photon in overcoming what's called the work function, and whatever is left over is kinetic. And what you need to understand or be able to do is connect all of this to Millikan's observations. Specifically, Millikan observed that the light has to have a minimum frequency. And the reason the light has to have a minimum frequency is that minimum frequency corresponds to the work function. So if the photon frequency is more than the minimum frequency, the photon energy is more than the work function, so the electron in the metal will be given more than enough energy to escape. The reason why more light striking the metal produces more electrons is simply because each photon in the light is absorbed by a single electron. So if you have more light, you have more photons. If you have more photons, you have more electrons being ejected. Finally, we have to be able to deal with the photoelectric effect equation, which is a construction of conservation of energy. Basically, you want to start by saying how much kinetic energy will an electron have when it leaves the metal. And we start off by saying it's given a photon energy of hf, and we take away the work function. So hf is the energy that the photon had before it was absorbed, and when the photon is absorbed, the electron gets all of that energy. W is the work function, and I see that I've highlighted this minus sign here, which tells me I'm going by memory. I think in your handout I had an equal sign there. It should be minus. So if we subtract the work function, we're left with the kinetic energy the electron has. Make sure you familiarize yourself with the different ways that this equation can go from here. EK can be 1/2 mv squared, or it can be QV stop. Both of these formulas use joules only. HF is the energy of the photon, so of course you can use HF or HC over lambda, and the formula for the work function is HF0. Graphical analysis of the photoelectric effect. One of the things that Millikan discovered is that when you do a photoelectric effect experiment and you plot the kinetic energy as a function of the frequency, is you get a line that looks like this. And one of the things he also discovered is if you use a different metal, you get a different line, but the line has the same slope. And if you use another metal, same thing happens. You get a parallel line. So what's changing here are the x and y intercepts, but the slope is the same. He discovered that the slope of this line is Planck's constant. Now, why is that the case? Well, if you take a look, and this is the threshold frequency, which we will get to. If you take a look at the equation of any straight line, which is y equals mx plus b, and you compare it to the photoelectric equation that we just developed, you can see some direct comparisons. One is that the kinetic energy is plotted on the y-axis, so the kinetic energy is the y-coordinate in the equation. The frequency is plotted on the horizontal axis, so the frequency is the x-coordinate. Well, by comparison then, it makes sense that the number in front of x is the same as the number in front of frequency, and that is the explanation for why the slope of this line must be Planck's constant. In addition, you can see that the y-intercept is negative w, so that means that this y-intercept will be negative w. Y is the kinetic energy, x is the frequency, the slope is Planck's constant, and the y-intercept is the negative of the work function. F0, of course, is the threshold frequency. So the slope is Planck's constant, the y-intercept is the negative of the work function, and the x-intercept is the value of the threshold frequency of the metal. We're going to talk now about X-ray production, which is actually the exact opposite of the photoelectric effect. What you need to remember for X-ray production is that high-speed electrons being stopped by a metal target produce X-ray radiation because each high-speed electron loses all of its energy and a single photon is created in its place. So what's happening is an electron energy is being converted to a photon energy. There are a couple of ways you can calculate an electron energy. One is 1/2 mv squared. One is q times delta v that's used to accelerate it. You can calculate a photon energy using hf. You can also calculate a photon energy using hc over lambda. And since this is a direct conversion of one form of energy to another, you can always develop an equation by setting any of the quantities on the left equal to a quantity on the right. So 1/2 mv squared equals hc over lambda would be a valid analysis here. Now we have to deal with wave-particle duality. I'm going to go through wave-particle duality in a more general sense first, then we'll talk about the specific aspects of it. So one side of the wave-particle duality coin says that electromagnetic radiation, which is typically thought of as waves, electromagnetic radiation behaves like particles. The specific point here, though, is that photons not only behave like a particle in that they are bundled together like a particle, but they actually have momentum, which is traditionally thought of as a particle property. The other side of the coin is that particles, true particles, pebbles, electrons, protons, alpha particles, behave like waves. They have what's called a deBroglie wavelength, which means when you pass these particles through a series of double slits, diffraction and interference occur, and you get an interference pattern. This is the formula that we use to calculate the momentum of a photon or the wavelength of a particle. So I like to call this formula the wave-particle duality coin. These other two formulas that are on your formula sheet in Physics 30 can only be used for photons. And the reason they can only be used for photons is they each make reference to the speed of light. And photons are the only things that travel at the speed of light. So you can't use those bottom equations for an electron, say, because an electron will never be traveling at the speed of light. Now we're going to break this down and talk about the Compton effect. The Compton effect is where photons exhibit momentum. The Compton effect occurs when a photon strikes a free particle. That word free means the particle, which is almost always an electron, is not connected to an atom. So this is different than the photoelectric effect. And that free electron is essentially at rest. What happens is the photon clips the electron and both of them are scattered. During the collision, what's going to happen is the photon will give some of its energy to the electron, but the collision will be perfectly elastic. There's no heat produced here, so if you found the energy of the incident photon, it has to be exactly equal to the energy of the scattered photon plus the kinetic energy of the scattered electron. It's perfectly elastic. It turns out that it's occurring in an isolated system, which means this collision is also one in which momentum is conserved. And during the collision, the wavelength of the photon will increase. If you take a look carefully at the diagram I've shown you, the wavelength of the photon afterwards is longer. The amplitude is less because it's lost energy, but it is a longer wavelength. And you should know, by the way, longer wavelengths mean less energy. That delta lambda can be found using what's called the Compton shift formula, which is on your formula sheet. H is Planck's constant, m is the mass of the scattered electron, theta, you have to be careful here, theta is the angle that the photon is scattered at. This formula is arrived at by using the laws of conservation of energy and momentum. One final note here, since the wavelength of the photon increases, if you wanted to find the final wavelength, you would take the initial wavelength and add delta lambda. This takes us to the final topic in this unit, which is the deBroglie wavelength, or Louis deBroglie's wave hypothesis, which says that particles behave like waves in certain situations. This has been proven by observations of interference patterns when we pass electrons through tiny openings. The electrons will diffract and interfere, producing an interference pattern on a screen. The de Broglie wavelength of a particle can be found by taking Compton's formula, which is this, and doing a little bit of algebraic arranging. We rearrange this for the wavelength, first of all. So we flip the coin over to the other side. We say to ourselves that something like an electron has a momentum that can be found using mv. So we put mv in, and that's how we find the de Broglie wavelength. The predicted wavelength from the above formula matches experimental data collected using Young's double-slit formulas. So you can be given, you're expected to know how to do problems where you have electrons that are accelerated by a voltage to a speed and then diffract. And you're expected to determine things like the angle of the n equals 2 interference pattern. You're simply going to calculate the de Broglie wavelength using this formula and then use that de Broglie wavelength into whichever of the two formulas below are applicable to the problem. Remember that this xd over nl is only good for small angles less than 10 degrees. And that is it for Unit 3. Hope you find that helpful. And I'm going to break here and do Unit 4 separately.